Let's present at research data security of IoT devices with limited resources, challenges and potential solutions by authors Ina Rozlomy, Andrei Yarmilko, and Sergei Naumenko. Embedded Internet of Things devices are compact, integrated devices embedded in various objects capable of collection, processing, and utilizing data, as well as exchanging it over a network without direct human involvement. However, the security of embedded IoT devices has become a key issue limitation their application. This problem arises from the imbalance between the potentially high functionality of such devices and their resource constraints. The architecture of embedded I/O devices is presented as the interaction of three main components. First component, sensors and actuators, components that provide data collection and transmission. Sensors gather information from the environment, temperature, humidity, etc., while actors perform corresponding actions during devices on-off. Second, data processor is responsible for processing and analyzing the collected data. This can be a microcontroller or a specialized computer systems. And the last one, network interface facilities communication with the external environment through various network protocols such as Wi-Fi, Bluetooth, LoRa, Zigbee, etc. The primary functions of embedded IoT devices include data collection, obtaining information from sensors, data processing, analyzing and processing the acquired data to perform defined tasks, and accurator control, sending signals to curators to execute specific actions. The typical properties of embedded IoT devices are accompanied by limitations that encompass the following aspects. First, competitively power embedded IoT devices have limited capability of complex computation due to restricted computational power. This may lead to constraints in applying advanced encryption algorithms and performing computation-intensive operations, reducing the device's security level. Second, memory. The limited memory capacity in embedded devices complexities the storage of a large amount of data and software. This may result in reduction of available resources for storing encryption keys, user data, and other critical elements, increasing vulnerability to attacks. The last one, power supply. Embedded IoT devices are often powered by anonymous energy sources or have limited power consumption. This limitation in power supply can lead to unforeseen interruptions in device operation or limit security capabilities. These limitations impact the capabilities of embedded devices in implementing robust security measures and pose a challenge in ensuring data reliability and protection. One of the key issues in the field of embedded IoT devices is the presence of vulnerabilities that can be exploited for attacks and security breaches. Integrate authentication and authorization. A lower level of authentication can serve as a starting point for unauthorized access to the device. The absence of robust user identity verification methods, the use of weak passwords, or simple authorization method can be entry points for cyber attacks. Second one, insufficient cryptographic protection. The use of weak or outdated encryption algorithms in I/O devices makes the data more vulnerable to interception and compromises. If encryption employs keys of influence, links of vulnerable to unknown attacks. And the last one, insufficient software updates. Limited memory in embedded devices can complicate the software update process. This could create a risk of temporary or permanent vulnerability of the device to new threats of vulnerabilities. Examining memory, energy consumption, and computational power, we can determine that memory limitation in embedded devices can lead to buffer overflows and constraint in strong encryption keys, complicating the cryptographic protection of information. Energy supply is a fundamental factor limiting the operational duration of devices and the risk of potential DOS attacks due to targeted expenditure of limited energy. Limited computational power complicates the application of complex encryption algorithms and may contribute to the execution of malicious code in case of influence input data validation. The discussed limitation expose risks that need to be carefully considered and adequately addressed in embedded I/O devices to ensure the reliability, confidentiality, integrity of the processor's data. Risks arisen from memory limitation. Energy consumption of embedded system may be influenced for the operation of cryptographic protection, both due to the design features of anonymous IoT model and intentional and unauthorized impact on their power components. Threats related to energy consumption pose a wide range of security risks for the system. Slide. This slide shows table which presents impact of embedded device resource constraints on information security. This analysis shows memory, battery charge, and energy consumption constraints significantly influence the cryptographic protection of information in IoT devices. Memory limitation often impacts the device's ability to store encryption keys and other essential data, increasing the risk of unauthorized access and information leaked. Meanwhile, battery charge limitation may lead in unauthorized disruption in the device's operation, reducing its reliability and the efficiency of protective mechanism. Finally, limited energy consumption can restrict the application of resource-intensive protective algorithms, particularly in the field of cryptographic security. Each of these aspects requires detailed consideration and analysis to ensure effective and adequate protection for embedded I/O devices. This diagram is presented on this slide describes the degree of impact of memory constraints on key storage, security management, and system vulnerabilities. Memory constraints in I/O devices can pose a significant risk to data security. On one hand, limited memory can complicate the storage of large amounts of data or complex software algorithms necessary for effective cryptographic protection. On the other hand, influencer memory can reduce the efficiency of key management, which is critically important for ensuring the security of communication processes. Memory limitation in our devices can lead in indicative storage and management of encryption keys, increasing vulnerability to attacks. Battery charge limitation in I/O devices can cause disruption in the operation, especially in critical situations. This may lead to failure to perform essential security operation and authorize access to data. Additionally, a low battery charge can limit the efficiency of encryption and other protection mechanisms. The diagram is presented on this slide illustrates the impact of battery charge limitations on the activity of security protocols, the risk of data loss, and constraints of protective mechanisms. The diagram shows that battery charge limitations have the most significant impact on the risk of data loss during interruption in operation. This underscores the importance of developing energy-efficient solutions to ensure the reliability and continuity of security functions. Limitation on energy consumption in IoT devices can be an obstacle to using resource intensive security algorithms, especially in the field of cryptographic protection. This may lead to the selection of less powerful and therefore less security encryption algorithms. Additionally, limited energy can slow down the processes of detection and responding to potential cyber threats. The difficulty of using complex cryptographic algorithms in IoT devices makes them vulnerable to advanced cyber attacks. The diagram is presented on the slides illustrates the impact of energy consumption constraint on the security of IoT devices. The diagram shows that limited energy consumption most significantly affects the selection and effects of security algorithms. This emphasizes the need for the development of energy-efficient cryptographic solutions that can provide the double level of security with constrained energy consumption. The percentage on all diagrams reflects estimated conclusion derived from expert opinions in this field. By focusing on key aspects of such limitations, such as memory, battery charge, and energy consumption, effective strategies can be developed to enhance the security level of IoT systems. Lightweight cryptography algorithms. Development and use of cryptography algorithms that require minimal resources for execution but still provide reliable data protection. Efficient energy management algorithms. Implementation of algorithms that optimize energy consumption without compromising security can ensure long device runtime and security system reliability. And memory socket optimization. Development of methods for effective utilization of limited memory space, including compact storage of encryption keys and using memory for security functions. Adaptive security mechanism. Creation of security systems capable of adapting to changes resource constraints to maintain an optimal level of protection in different operation conditions. Improvement of authorization algorithms, implementation of effective authorization algorithms that provide a high level of security with limited complete resources. And the last one, security communication protocols. Development of specialized communication protocols for IoT that are optimized for efficient resource utilization and ensure reliable data protection. These strategies form the foundation for ensuring the security of IoT devices operation in resource-constrained environments. In the context of ensuring security for IoT devices with limited resources, it's important to recognize that effective security requires a multidimensional approach. This approach should involve the integration of technical innovations and strategic planning. Considering the constraints in memory power consumption and computer power, the development of lightweight cryptographic algorithms that utilize minimal resources becomes a priority to ensure reliable data protection. Security systems should be flexible, adaptive, and capable of maintaining a high level of security despite resource limitations. This includes not only technical aspects but also operation resource management, especially concerning energy and memory. Thank you for your attention.